We left off last Thursday with our Unit 1 test. You may have noticed that those are graded and posted in Blackboard for you. Just like with any of our quizzes.
Mr. Hoff, your microphone got real quiet.
Here, is that better?
Not really.
No?
Started off, it was great, and then it just reduced in volume.
I wonder if it did that. Let me try this. Is that any better?
No.
No? Is it in both rooms?
No, we can hear you good.
Okay, so it must be just 162. Sometimes when it cancels out the background noise, it mutes or tones down the speaker volume as well.
Oh, I back it up so we can try that out.
Is that better?
Yeah.
Okay, perfect. So for the Unit 1 test, you can do corrections just like on the quizzes. So make sure you're doing those. Any corrections for Unit 1. And of course, quizzes basically 1 through 5. All the quizzes from Unit 1 must be in by, we'll give you till Monday. What is that going to be, September 21st? So a week from today. So that gives you time to do corrections on the test. And if there are any of those quizzes from Unit 1 that you need to do corrections on, you can still do those for one more week. If you need help with them, let me know. I'd be more than happy to either meet before class or stay after class sometime and work through the problems with you if I need to. But I want you to be able to, first of all, I want to make sure that you have the right way to do the problem down somewhere so you have it to go over. And second, I want you to get back as many points as you possibly can. Okay, so today we're shifting gears to start Unit 2. Unit 2 is on measurement. There are a lot of different things we can do with measurement, and we're going to do a few different things. We're going to look at measuring devices. We're going to look at units of measurement, and then we're going to look at areas, volume, surface areas, basically applications of those measurements. Today we want to talk a little bit about history and origins of measurement. Measurement really came from a need to communicate. If you and I were both trying to build the same object, we're trying to build one object or two objects, but we want them to be identical. Well, if we're in the same room together, that's not such a big deal. You can walk over to where I am working and mark off, the same size, or I can come over to you, whatever. But if you're down the hallway or across town, there needs to be some way to communicate that. And it'd be nice to be able to record it for later so that later on we could rebuild the same thing and make it identical to what we built before. So it came down to measurement. Well, what came of it was they'd take something. Let's say I wanted to communicate the size of this sheet of paper to you. I would take my pen and I would hold it up and I'd say, okay, there's 1, 2. That sheet of paper is just a little bit more than 2 pens long. You can see the pen doesn't quite reach the top. Well, so it comes down to you and you take your pen. Notice it's a different pen. You go 1, 2. Well, 2 pens actually is longer than the piece of paper. So you end up with something considerably larger than what I had, even though you did the exact measurement I told you to. So for measurement to be accurate, be useful, 2 things had to take place. Both people doing the measurement have to have that object, and the objects must be the same size. a little bit difficult to see. I'll hold it up to the window in the background here. You can see those pens are not the same size. The one pen is considerably longer than the other. Not an effective measurement tool. If you have this one and I have this one, we're not going to be speaking the same language, or our measurements are going to have different meanings. So we have to have things that had the same size. Later on, we'll talk about what they used for those measurements. They chose things that were handy to them. But today I want to talk about, once we have those units, how were they actually used for measuring? Well, they started out just like I did with a piece of paper, taking the pen and moving it up and counting. But that very quickly became tedious and slow. So they developed measuring devices. So I might take my pen and lay it out on that measuring device and say, there's 1 pen, 2 pens, 3 pens, and marking it out that way. And that's our first rulers. So now let's measure something with this ruler. Of course, we all know that we take the 0 end. This is the 0 end because that's the numbers that's the end that the numbers start from. We line whatever we're measuring up with that end. And we go to see where it ends on the other end. This object here, with this measuring device, would have to be said to measure 2 units. In this case, 2 pens. Well, you might say, well, it's pretty close to being right in the middle. Can't we call it 2.5? Well, the honest answer is no, we can't. Because if we write that measurement down as 2.5, we are saying something about the measuring device, or something about the measurement itself that isn't true. Part of measurement is reporting the size of the object, but it's also reporting the capability of the measuring device that we're using. So let's measure this green line here as well. Now you would say that the green and the blue lines are not the same length, but with this current measuring device, both of them would measure 2 inches because that's what they're closest to. Precision of a measuring device is the ability to distinguish between similar objects. So the green and the blue line here are similar in length, but they're not the same length. However, this measuring device is not precise enough to tell the difference between them. Well, how do I make it more precise? Well, the easy way is to cut my units in half. Well, unfortunately, both of those are still closest to 2.5 units. So cutting them in half did not do the trick. So I can come back and cut each of those in half. And now I would say the green one is closer to 2.5 units, and the blue one ever so slightly closer to 2 1/4 units. So now this measuring device is finally precise enough to tell the difference. Which brings us to something called the degree of precision of a measuring device. The degree of precision of a measuring device is simply the smallest unit, or smallest division on the measuring device. For this measuring device, that smallest division is 1/4 of a unit. So that's the degree of precision of this measuring device. Now you might wonder, why did we use halves and quarters and 8ths and 16ths rather than using tenths? Would have been a whole lot easier if we'd used tenths. Well, because it was really a technology issue. At the time, if this was 1 unit, my length of my paper was 1 unit long. If I wanted something smaller, cutting it into tenths was difficult, but a half was easy. I just fold it over, there's my half. fold it again, and I have quarters. And that was really the most reliable, precise technology they had at the time, was folding. So that's why we ended up with halves, quarters, eighths, sixteenths, and so on. Now, for each of these measurements, these are not exact. Measurements are never exact. There's always some form of error in a measurement. If we look up here, the blue line is not exactly 2 1/4 units. It's just closest to 2 1/4 unit. With this measuring device, anything between here and here would have been called 2 1/4, because anything in that red range would have been closest to the 2 1/4, which means that there is some sort of a built-in error or possible error built into every measuring device. For this measuring device, the possible error, well, it could be from here to here away and still be called 2 1/4 units. Well, how far is that? It's 1/8 of a unit. It's half of the distance to the next division. So the possible error in a measuring device is always half of the degree of precision. So for this measuring device, the degree of precision was 1/4. The possible error, 1/2 times 1/4 is 1/8. So the possible error here is plus or minus 1/8 of a unit. So anything measured with this measuring device is really only, could be off by as much of an eighth as an eighth of a unit. Or it could only be measured to the nearest 1/4 unit. So on this measuring device, can somebody tell me what the degree of precision is? What's the smallest division? What's this division equal to?
8.
1/8. Now, just to make it easiest, I'm going to label this as inches for now, so that we can put a unit that we're familiar with. So 1/8 of an inch is our degree of precision. So then, can somebody tell me what the possible error is in this measuring device?
16.
A 1/16 of an inch. Good. Plus or minus a 1/16 of an inch. We get that by doing 1/2 times our 1/8. 1/16. Because of this built-in error, every measurement that is stated using this measuring device is really stating a range of possible measurements. So let's give you a stated measurement. Let's do this. The stated measurement is 1 3/4 inches. Well, the actual range of that measurement, 1 3/4 inches is saying here's 1 3/4 inches right here. Whatever we measured was closest to that, so somewhere in that purple range there. That range goes from our measurement, 1 3/4 inches, minus our possible error of a 1/16 of an inch. So 1 3/4 minus a 1/16, 1 12/16 minus a 1/16 is 1 11/16 inches. up to our measurement of 1 3/4 inch plus our possible error of a 16th. So again, 1 12/16 plus a 16th of an inch is 1 13/16. So with this measuring device, when I state a measurement of 1 3/4 inches, what I really mean is that whatever I was measuring is somewhere in that range, between 1 11/16 inches to 1 13/16 inches. Because that's the degree of precision that measuring device is capable of. It can't get any closer than that. Anytime we make a measurement, no matter how precise, how small of a unit we use, the measurement that we are using is a range. It's approximate. There's errors in it. Always, no matter how precise our unit of measurement is. So, I want you guys so I'm just labeling the first inch here. It is stated that using this measuring device, an object measured 3 1/2 inch. Find that implied range of that measurement. I'll give you a minute in your notes, see what you come up with, and we'll go over this in about a minute. So in order to find that range, we have to start out with the degree of precision. What is the degree of precision on this measuring device? Well, if we count the spaces between 0 inches and 1 inch, there's 16 spaces. So that means each space is a 16th of an inch. Should have labeled this as inches again. So if my degree of precision is a 16th, what's my error? Come on, somebody be brave.
30 seconds.
There we go. Thank you. 1/32 of an inch. So our possible error is plus or minus a 32nd of an inch. So then our range from our stated measurement of 3 1/2, we have to subtract a 32nd of an inch, which is going to be 3 15 32nds, up to our stated measurement of 3 1/2 plus a 32nd of an inch, which is going to be 3 17 32nds. Any questions on that? So when we have fractional measurements like that, we must have some sort of a knowledge of the measuring device. We don't necessarily have to see the measuring device like we did there. We might have something like this. We might be told that we have a measuring device with a degree of precision of 1/8 inch and a stated measurement of 4 1/4 inches. From there, we can still construct that range. We know, of course, our error will be plus or minus what here?
16th.
16th, good. Plus or minus a 16th of an inch. So then our range will be our measurement of 4 1/4 minus a 16th, which would be 4 3/16, to our measurement of 4 1/4 plus a 16th, be 4 5/16. When we are doing calculations with these measurements, we need to account for the fact that that measurement is not exactly 4 1/4, that it's somewhere in that range. Now, fortunately for us, we're typically going the other direction. You're going off of a blueprint or a design drawing where the measurements are labeled and you are creating the object from that measurement, which is nice because you don't have to worry about using the errors in calculations. But what you do have to be aware of is, you're given plus or minus a 32nd or a 64th of an inch if you're making furniture. That's pretty standard to do a 64th of an inch. Or companies that are doing decimal inches, a 100th of an inch. I believe Mastercraft has gone to a 100th of an inch tolerance on their measurements. But if you're cutting an object and you're consistently off, let's say you're doing a 64th of an inch, you're consistently short by a 64th of an inch, that can still cause problems in the end, because if you're always short by that same amount, it builds up and the overall length will be off by considerably larger. So we still have to account for the idea that measurement and cutting are not exact. You don't want to cut everything short. You want to be, varying around that desired length. Quality control, I'm getting a little bit off topic here, but you have a desired size or desired length. The ideal situation is that if that's your desired length, that all your cuts will look like this. The height of that brown curve is the number of cuts that are made of that length. So if the black line is your desired length, you see that the curve is highest right at that black line. So our hope is that most of your cuts are really close to it. But then we'll have some that are too short, some that are too long, but it'll be evenly balanced out. You'll have just as many that are cut too long as you do that are cut too short. That's called the normal curve, or some of you may have heard it referred to as a bell curve. That's the desired natural state of any sort of process, any sort of quality construction is to be like that. If you're consistently on one side of the line or the other, you're not canceling out your errors. Well, not all of our measurements are given as fractional measurements. We can have decimal measurements. We had maybe even mentioned this one a little bit in the last unit. If I have something that listed as 23.2 inches, or if I list it as 23.20 inches. Is there a difference between those measurements? Mathematically, there is none. Mathematically, 23.2 and 23.20 are the exact same measurement. They're the exact same number, at least. But when we're talking about measurement, there's more to consider than just the numerical value. So if I take a section of a ruler here, the 23.2, that is implying that I have a ruler that is capable of measuring to the nearest tenth of an inch. And whatever I was cutting happened to be closest to 23.2, somewhere in that range. This is implying, the way we have that written, a degree of precision. The implied degree of precision in that measurement is the place value of, I usually say the last digit, but technically it's the last significant digit. We'll talk about what significant digits are here in just a second. That place value of that last digit is the 10th. So that is implying a degree of precision of 0.1 inches, which, as you can see by the red line I put down here, gives us a possible error of plus or minus half of a 0.1 is 0.05 inches. That's implying a range, if I subtract 0.05 of 23.15 inches to, if I add 0.05, 23.25 inches. That's a pretty significant range. On the other hand, this one over here, 23.20, that is implying that I have a measuring device that is capable of measuring to the 100th of an inch, and it still just happens to be closest to 23.2. So that's implying a range, I'll do it in purple here, from here to about here. Obviously, that's a much smaller range. That is implying a degree of precision because that last digit is in the hundredths place of 0.01 inches. So then our error is plus or minus 0.005 inches. So that's implying a range here of 23.195 inches to 23.205 inches. We see a much smaller range. Now, the big moral of the story that I want you to get out of this is you can't just haphazardly throw zeros at the end of your measurement. You might look around and see that everything else in your drawing or whatever is measured to the 100th of an inch. Unless you truly had a measuring device, a ruler or tape measure that went to the 100th of an inch, you cannot report it as a 100th of an inch. If your ruler only goes to the 10th of an inch, you can only report your measurement to the 10th of an inch. Throwing that extra zero on the end may seem harmless, but it might say something to somebody else down the line looking at your measurements and trying to use them for something else. Now, with that said, I will admit this is more of an engineering and architectural application than it is a on-the-ground, on-the-job site construction application. But it is something you need to be aware of to work with architects and report information to architects for them to use when you're working on the job. If you ever end up being a foreman or a job site layout person, you're going to have to be aware of how you report those measurements back to any sort of designer. So this brings us to a conversation of something called significant digits. One of my least favorite lessons to teach in the course is significant digits, because it's one of those that it's actually a very important topic to be aware of, but it's very difficult to see the importance at the level you're working at. Like I said, it's something it's definitely, if you're in engineering, significant digits are vital. If you are an engineer and you are not using your significant digits correctly, you can create some major issues. That applies for architects and designers as well. You might ask, well, if I'm on a job site building a home or building a cabinet, how important is it? Well, you need to be able to read significant digits, and that's about it. But at the same time, the hope is that through the years, you're going to move up into one of those design and engineering positions at some point. Trust me, as somebody who thought I was going to be on a job site forever, it doesn't work out that way. A few years ago, I got to the point where I couldn't even do my summer construction anymore because the body wouldn't take it. Happens to the best of us. So significant digits. For a digit to be significant, a digit is significant if it is not a zero. So if I give you 230 inches, that has 2 significant digits. SD is the abbreviation I'll use for significant digits. That 0 is not significant. I have 0.053 inches. Same here. Those are, the 5 and the 3 are significant. Those zeros are not significant. So that again has 2 significant. Zeros are significant if they meet one of 3 criteria. The first is if they are between other significant digits. What does that mean? Well, that means if I have 304 inches, that 3 and the 4 are significant because they're not 0. Well, this 0 is between other significant digits, so it is significant. So that number has 3 significant digits. Our measurements don't have to be in inches. We could have 7,020 millimeters. Well, again, the 7 and 2 are significant. This 0 is between other significant digits, so it is also significant. This 0 here is not. It's not between other significant digits. So that has 3 significant digits. I'll put it up here. We might have 0.05025 inches. Again, we've got the 5, the 2, and the 5 are significant because they're not 0. This 0 is between other significant digits, so it's significant. The other ones are not between other significant digits, so they're not. So this has 4 significant digits. A 0 can be significant if it is indicated. What does that mean? Well, indicated would be I say something is 200 inches, the way I have to read that is that my measuring device, I have to do what's called worst case scenario. I have to assume the worst. If somebody reports it as 200 inches, I have to assume that what they were measuring was only to the nearest hundredth of an inch and that those zeros are not significant. That only has one significant digit. But if I report 200 like this, I either put the bar below or above. If I do it like that, that is indicating that that zero is significant. So this is saying that has two significant digits. Or we might have 200 like this. Of course, this one up here is saying that we measured to the nearest 10 inches, and it happened to come out the closest to 200. Here, if I put the line above the zero, this is saying we did measure to the nearest inch. It just happened to come out closest to 200. So that has one. This is significant because it's indicated. Well, this zero is between other significant digits, so it's also significant. So that has three significant digits. The last one is the difficult one, the one that's hard to interpret. Numerically unnecessary. What does that mean? Well, in the number 200, these zeros are numerically necessary. They have to be there. If I take them out, they change the meaning of the 2. If I take them out, well, 200 becomes 20 or just 2. That's a very different meaning. Those are numerically necessary. Because they're numerically necessary, we assume they are not significant unless they're otherwise indicated. Likewise, we might have 0.035 inches. These zeros, well, this first one doesn't mean anything, but this zero here definitely is numerically necessary. If I take that out, that changes from 35 thousandths of an inch to 35 hundredths of an inch. Very different meaning. So because it is numerically necessary, it is there to give meaning to the other digits. We have to assume it's not significant. So this is where we have to get over our previous beliefs on the word significant. The word significant, most of us say, well, significant means important. Not necessarily in this case. The word significant means it has meaning to the measurement, but not necessarily important. These zeros here are all very important because if I take them out, it changes the meaning of the number. But they're numerically necessary. So we have to assume that they're not part of the measurement unless we're told they are. So what do I mean about numerically unnecessary? Well, that goes back to this thing. This zero on the end here is not necessary. If I take that zero off, it doesn't change. 2.7 and 2.70 numerically mean the same thing. So that zero is not necessary. So because it is not necessary, then we will assume it is significant or is part of the measurement, which is what significant means. The only reason to include that zero is because it's part of the measurement. So we can assume that that one is part of the measurement. Where all these other ones, we can only include them as part of the measurement if we are told they are part of the measurement. So this leaves us with kind of a a tedious little task here of defining or determining how many significant digits a number has. This number here has the 4 and the 2. Those zeros are not significant. That has 2 significant digits. This number here .03070 inches. Well, the 3 and 7 are significant because they're not zeros. This 0 is between other digits, so it's significant. This 0 is numerically necessary. If I took it out, it changed the meaning of the other digits, so that we cannot assume it's part of the measurement. It's not significant. However, this one here is totally unnecessary. 0.0307 would numerically mean the same thing as 0.03070. Because of that, the only reason that it's there is we have to assume it's part of the measurement. So that has 4 significant digits. Basically, when we say numerically unnecessary, what it generally means is after the decimal and at the end of a number. Like this 0, it was after the decimal point and it was at the end of a number. This 0 was after the decimal point and at the end of a number. This 0 is after the decimal point, but it's not at the end of the number. So that was not significant. This 0 is at the end of the number, but it's not after the decimal point. So it is not significant. Now to change that up a little bit, if I put 4,200.0 inches, the 4 and 2 are significant. This 0 is both at the end of the number and after the decimal point, so it's significant. If I took it off, 4,200 and 4,200.0 have the same meaning. If I take it off, it doesn't change anything, so the only reason for it to be there is because it's part of the measurement. Then, of course, these other zeros are between significant digits, so that has 5 significant digits. This is one of those concepts that I'm not expecting you to be an expert at. I'm not expecting you to be tremendously fluent at it. But it's something that I want you to be able to understand as you're reading calculations by an architect or a structural engineer. You need to understand, why did they all of a sudden go from 14.2 to 320? Why all of a sudden did they lose the decimal places? It's because they're working with significant digits. Okay, for right now, I'm going to give you a little bit of time to work here before break. We've got about 5 minutes before break. I'm going to give you, where are we here? This is in the big book. On page 266. I'll put the 2 in there. This is exercise 7-4. 7 through 17. What I just want you to do for now is look at them and tell me how many significant digits each of them has. Actually, I give you the right page. I did not give you the right page. It's actually page 268. Exercise 7-6. 7 through 25, the odds. So I'll give you the last few minutes here, the first hour, to work on those. I'll be on the network here for questions. We'll take a break in a few minutes, then we'll come back and we'll talk a little bit more about how these are used.
Who's gonna do these?
Well, if you want to take a 10-minute break, we'll be back at 1:30 and we'll pick up from there.
Bird breaks. Oh, they're all over here. Those chairs up down.
You go to the bathroom now?
garage, so I'll see if I can get a drink back this weekend. I can't drink it all because my sister won't be back until like October. Tough, Alex. We're just going to have to pay for it this summer. The only thing I had to pay for is now business. Just go to McCain's when they came around. I did this one. So I didn't pay him the first time for his first day. Because, where do we go? I said I could pay. Here's literally just an armful. Yeah, pretty much drank the whole cooler. Here's also soccer. And how quiet it is. Oh shit. That night was. Complicated. Thanks. Okay, through that night. I had to already. Driver. I was like, alright, I'll drive you up there. There was this huge freaking hole. Yeah. Right, I was not sure like, with that hole, I was like, oh, boom. Drop my cock in the hole. I swear I was going to say, what are we supposed to be testing? Every time I had to go, I went water because my chill.
I'm guessing it'll be like me.
Video, yeah, the four-wheeler won't start. I'm walking home. All I want to do is bring a jack and bring blocks and have some in the car and get up all the roll around.
How's it going, guys?
What's going
Hi. Oh,
I dropped my phone. I can't believe I can set up the sauce now. I still can't believe graduation. For 3 hours waiting for sleep. I would have. If you need the food, I ran like a. Yeah, I don't think. I don't know where you was at. You want to hear a really bad joke I heard? Cars that showed up that night. Andrews. And ran like, and one of my friends using the tent of this girl that was just plastered. So he was.
very nice.
Oh, he was, but not that. That was Dylan. And like, he was like, I gotta go to the concert here. So he goes up the tent. There's a cop right outside the tent. And he looks at him, and the cop was like, "Don't run." He turns around and starts running. The cop was like, "Get back here." He was like a couple of feet away from the cop. That was rough. I was running so freaking fast, and I hit a barbed wire right above the dies. That's all once. I forgot the dark now, bro. That would only took me about an hour. Probably like 15 minutes away from Barron. And there was a couple kids that ran all the way back to Barron. Okay, it's like that's a little excessive, but. Car was up there. My car was parked right next to the fire. They didn't even do it. Like caught about half of this. Next time, dude. Lights out. Yeah. Relocked it. We cost busted it. They gave out over 200 underages. I guess the cops are at this party for so long, so there's people that weren't 18 there, so all their parents waiting for them to come get picked up. And I was running through the wet fields and everything, so I was so I had to lay out there and it started getting windy and I was just free. They called me. Can they do anything? You're oh, probably can't. There's one. His freaking brother.
And was it Lorenzo?
Yeah.
Weren't they watching people though? Like Andrew was watching Caitlin. Lorenzo was. I don't think he did.
But those cops must have been blind or they didn't care because there was a bunch of weed. After the cops showed up, it was just sitting over there. He snuck over there and threw it in the brush. They never even saw it. That's all they just had. I could tell I was drunk on the run out there, but I wasn't on the way back because the thorns and shit hurt a lot more on the way back.
Okay, it's that time, so let's go ahead and get rolling here again. So I want to start talking about the ideas of precision and accuracy. We talked a little bit about precision already in the first hour, where precision is the degree of precision or precision of a measuring device is the ability to distinguish between objects that are similar in size. It has to be precise enough to get down to those differences. Accuracy is how close we are to a desired size, a desired amount. So if I looked at my target I drew over here, we have blue dots. We have a set of 6 blue dots and a set of 6 green dots. Those blue dots are more accurate because they are closest to the desired target. Precise is repeatability. Precision is repeatability. The green dots, even though they're not close to our desired target, they're very, very close to each other. They're very repeatable. We could count on consistently getting the same result or very, very, very near the same result each time. Another definition of precision is the result of a process, how close it is to the result of the previous process. Now, our desire, obviously, in anything we do is to be both accurate and precise. We've already talked about precision in our measured numbers as being the place value of the last significant digit in the number. So if I give you a measurement of 230 inches, the precision there is the nearest 10 inches. If I give you 0.70 inches, the precision there is to the 100th of an inch. The place value of the last significant digit. Accuracy is a little bit less obvious. Accuracy is simply the number of significant digits.
I heard it from not here.
Yeah. The theory here is if you want to get closer to what you want to be, you go down to one more order of magnitude. You go add another significant digit. So this number here, 230, only has 2 significant digits. It has an accuracy of 2 significant digits. Where this number here has 3 significant digits. So we would say it has an accuracy of 3 significant digits. Now there are tiebreakers out there. If two numbers have the same number of significant digits, every textbook has a different way of breaking the tie. If I ask you which number is more precise, but they both go to the same place value, they say that the larger number is more precise in most cases. If they say which one is more accurate, and they both have the same number of significant digits, they generally say that the one that's the most precise is also the most accurate. For our purposes, I'm okay with saying if they have the same number of significant digits, they have the same accuracy. Or if they go to the same place, you have the same level of precision. I'm not concerned about breaking the tie, but there are little, each textbook you get to different little tiebreakers for. The reason we want to define precision and accuracy is so that we can do operations with our numbers. Addition and subtraction. If you go back to that first day when we were talking about addition and subtraction, we said we first of all, we have to have the same names, we combine the counts, and then we keep the same name. Remember, having the same name and keeping the same name is all about the place value. Addition and subtraction preserve precision. About the least precise number. So if I have an example of 23.7 inches plus 8.44 inches. Well, if I add those numbers together, I get 32.14 inches. However, I can't report my answer like that. I have to round to the proper number of significant digits. If I leave my answer here as 32.14 inches, I am implying to somebody else who reads that calculation, reads that measurement, I am implying that all of my measurements were done to 100th of an inch. They were not. If I look over here, I see that this one is precise to the 10th of an inch. This measurement's precise to the 100th of an inch. The least precise is the 10th of an inch, which means I have to round my answer to the 10th of an inch. So the 10th place is the 1. The next digit is the 4. That's telling me this day is 32.1 inches. Now you might ask, how is that better? How can it possibly be better to round that off and report it as 32.1? We just lost 0.4 of an inch off of our measurement. How can that possibly be better? Well, because it's not necessarily better or closer to correct. What it is it's more honest. Because the error in this measurement over here, because its precision is to the 10th of an inch, it's plus or minus 0.05 of an inch. The part that we rounded off here, the 0.04 of an inch, is smaller than the error in this measurement. So that's why we have to round to the least precise measurement when we do that. Subtraction's the same way. I might have 52.43 inches minus 27.6 inches. I do my subtraction there, I get, what, 24.83 inches? Well, again, that's the correct number mathematically, but for the purposes of the measurement, I have to make sure I'm reporting this result in a fashion that other people understand how precise my measurements are. What's the degree of precision on this first measurement here? That is the 100th place, right? The 0.01 inches. What's the degree of precision on this measurement? 10th, perfect. 0.1 inch. The least precise, the lesser precise, is the 0.1. So I have to round my answer to 0.1. So there is my 10th place in my answer. The next digit's a 3, so that's telling me that stays 24.8 inches. Where it can be a little confusing is if we get into larger numbers. You know, these are all decimal numbers. It's not so bad. We can kind of see why it's okay to round that off because of the error size. But if we have 7,200 inches, let's do this. Let's do it in metric here. Makes more sense to do 7,200 millimeters plus 345 millimeters. 7,200 plus 345 is 7,545 millimeters. What is my degree of precision in this measurement? That's the hundredths place. Those zeros are not significant because they're not indicated. So this is precise to the nearest 100 millimeters. How about this measurement? Nearest 1, so that's the 1 millimeter. Well, the least precise is hundreds. That's way less precise to be to 100 millimeters. So I have to round to my hundreds place, which is right there. Next digit's a 4, so I don't have to round up. So it's 7,500 millimeters. Now, we lost a lot of information, but remember, this measurement here is technically plus or minus 50 millimeters. So another thing that's important to take out of this is if you do have a measurement that comes out exact like that and has zeros, if you really did measure to the nearest millimeter, you do need to make sure you indicate that 0. So designers know that you did measure that precisely. They don't just assume the worst. I might have 2,345 millimeters minus 1,842 millimeters. So I subtract here 2,345 minus 1,842. I get 503 millimeters. I look at my precision. This one is precise down to the nearest 1 millimeter. This one is precise down to the nearest 1 millimeter, which means I can leave my answer to the nearest 1 millimeter. I don't have to round that answer. I want you to try this one in your notes. 650 millimeters minus 248 millimeters. We'll go over it in about 30 seconds here. So for that one, when we subtract 650 minus 248, we get 402 millimeters. We look at our degree of precision. This one's precise to the nearest 10 millimeters. This one to the nearest 1 millimeter. The least precise, lesser precise, is 10 millimeters. So I have to round this to the nearest 10. Well, the 0 is in the tens place. That 2 tells me that stays a 0. So it's going to round to 400 millimeters. However, that is not my answer yet. Because the tens place here is a significant digit, I have to make sure I mark that 0 as being significant. So that tells whoever's reading this that this is calculated to the nearest 10 millimeters. Just happened to come out to 400. Another one that's really strange is one like this. Let's take something like 2,400 inches minus 12.3 inches. So we subtract there, 2,400 minus 12.3 is 2,387.7 inches. However, when we go to analyze our significant digits, this measurement is only precise to the nearest 100 inches. This is precise to the 1/10 of an inch. So the lesser one there is the 100 inches is less precise. So my answer has to be rounded to the nearest 100 inches. The 3 is in the 100 spot. That 8 tells me to round up. I end up at 2,400 inches. Here I subtracted, and I ended up with the same number I started with. The reason that happened is that this 12.3 inches that I'm subtracting is smaller than the error in this measurement. This measurement's really plus or minus 50 inches. Technically, it's inappropriate for us to subtract 12.3 inches from 2,400 inches if that 2,400 is only precise to the nearest 100 inches. Because like I said, what we're working with here is smaller than the error of this measurement. Engineering term would be that there are different orders of magnitude, so we shouldn't try to combine those numbers. But it can happen. We may run into some in the homework or quizzes where that does happen. Multiplication and division. Remember, we said when we multiply or divide, we do not need the same name. We combine the counts, but then we also combine the names. So for multiplication and division, what that comes down to is preserving accuracy. How does that work? If I have 3.2 inches times 21.4 inches. Multiply those out. 3.2 times 21.4. 68.48 inches times inches is square inches. Inches squared. We combine the names. But we're preserving accuracy. Remember, accuracy is the number of significant digits. So this first number here has 1, 2 significant digits. This number has 1, 2, 3 significant digits, which means my answer can only go to 3 significant digits. 1, 2, 3, and we round it off there. That 8 tells us that it has to round up to 68.5 square inches. So we rounded it off according to the number of significant digits in each of the original numbers. Oops, sorry. We couldn't round to 3. We have to round to 2, the least number. So 2 significant digits would be right here. So that 4 is telling us that stays at 68 square inches. So it appears as though that result is less precise than the 2 inputs. And it kind of is, but remember the units are different. When we're multiplying or dividing, we're also combining the names. We're also combining the units. So this is only precise to 1 square inch, where these are both precise to 1/10 of an inch. We might have 5,380 inches times 2.4 inches. So again, we'll multiply 5,380 times 2.4. We get 12,912. And again, that's going to be inches squared. But once again, we have to look at our accuracy of each number. This is accurate to 1, 2, 3 digits. That has 3 significant digits. This one has 2 significant digits, which means we have to round our answer to 2 significant digits. 1, 2, we got to round it there. The 9 says that rounds up to 13,000. So we would report that answer as 13,000 square inches. I might have 360 square inches divided by 0.18 inches. I do 360 divided by 0.18. I actually get 2,000. Square inches divided by inches would be inches. But now I have to make sure I properly indicate this. This number had 2 significant digits, so it is accurate to 2 significant digits. This number also had 2 significant digits. I have to make sure I report my result to 2 significant digits, which means I have to indicate that first 0 as a significant digit. I might have 34.2 inches divided by 15.36, or 34.2 square inches divided by 15.36 inches. 34.2 divided by 15.36. I get 2.22656. And of course, square inches divided by inches is just going to be inches. But again, I have to worry about where I've already rounded it off because I know I'm not going to go any further than that. But I have to round it off to the proper significant digits yet. This number has 3 significant digits. This number has 4 significant digits. The smaller of those 2 is 3 significant digits. So my answer is going to have to be rounded to 3 significant digits. So 1, 2, 3, I will round it there. That 6 tells me to round up to 0.23. So 2.23 inches is my proper answer for that. Now, I realize this is not something you're going to do every day. This is not something that some of you may never do this. There might only be a few of you. There might be a lot of you that move up into design and engineering positions. There might not be any of you. You might be very happy working on the construction crew and not move up into those positions. So I realize that for many of you, this is one of those things that you might use someday, but you're not going to use right now. I understand that. I'm not going to make a big deal about it. There will be a quiz on it, and there will be a few problems on a test. I will make sure that you are well prepared for those problems. That we'll do something to make it so that you, right before you take the test, that you are well capable of doing the problems I put on there. For right now, I want you guys to try a few in your notes. I want you to combine each of these using the proper number of significant digits. So for number 1, 2.48 inches plus 79.7 pounds, or 7 inches, I should say. Number 2, 3.5 inches times 6.48 inches. Number 3, 52 pounds divided by 4.83 square inches. And number 4, 17.24 inches minus 5.368 inches. Do those 4 in your notes. We'll go over them in a couple of minutes, and then we'll pick up from there. Let's take a look and see how you did here. So the first one, 2.48 plus 79.7 is 82.18 inches. But now to round that, this goes to the hundredths, that's 0.1 inches. This goes to the tenth, or so 0.01 inches. This goes to the tenth, so 0.1 inches. Least precise is the tenth, so we got to round that 82.2 inches. This next one here, 33.5 times 6.48 is 22.68 inches squared. This one, however, remember it's multiplication, so we go to the number of significant digits. This is 2 significant digits. This is 3 significant digits. So our result can have the lesser of those, which is 2 significant digits. 1, 2, we round it there. That's going to be 23 square inches. Next one, 52 divided by 4.83. Give us 10.766. That's going to be pounds per square inch. But again, we have to look at our number of digits. This has 2 significant digits. This has 3 significant digits. The lesser of those is 2, so we're going to round to 1, 2 significant digits. The 7 says we round up to 11 pounds per square inch. And finally, the last one down here, 17.24 minus 5.368 is 11.872 inches. Now we're subtracting, so it goes to place value. This is precise to the hundredths place. This is precise to the thousandths place. Less precise is the hundredths place. We round to the hundredths here, 11.87 inches. Now, I don't expect you guys to be experts at these. The biggest thing is if you look at solutions manuals and things like that, many of those are written by engineers, so they do round their calculations to significant digits. So it might help you understand how they're rounding as you read through those. Like I said, I'm going to give you some homework on it, and we will have a quiz on it, and there will be a couple problems on the test. But it's not one of those topics that I'm really going to push hard at you. So out of the big book, we're going to do pages 266, 267, 268, and 269, and 270. Starting with exercise 7-4, 7 through 17 the odd. 267 is exercise 7-5, 7 through 17, the odds. 268, I already gave that one to you in the first hour. Exercise 7-6, 7 through 25, the odds. Page 269 is exercise 7-7, 7 through 21, the odds. And page 270 is exercise 7-8. 7 through 21, the odds. I don't know why I wrote odd in those last two and not the others, but there we go. So I'll let you guys have the last 15 minutes here to get started on those. We have a little bit more to talk about errors and stuff next class, and then we will have our quiz on this stuff coming up on Wednesday, just so you're prepared ahead. Any questions? Okay, I'll shut off the recording and I'll let you guys work. I'll be on